Okay, it's working. Yes, it's working. Okay, so I would like us to plug in -2 here and just give me the sign. Then I would like us to plug in -0.5 and give me the sign. Then 0.5 and give me the sign, and then 2.5 and give me the sign. So let's start with -2. Negative, 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 negative. 1, 2, 3 negatives. I need the sign here. Very good, thank you. Of course. Good. With -0.5, negative, negative, but positive. -0.5 plus 1, 1 overtakes it. So negative and negative. Sign. Good. For 0.5, positive, negative, positive. For 3, positive, positive, positive. So if I ask you what does the function do between -2 and -1, as well as between 0 and 2, what will you say? What is the function doing? Very good. Awesome. It is indeed decreasing. What does the function do between -1 and 0 and 2 and 3, according to the derivative? Increase. Excellent. I agree with it. I saw it in the chat. Yes. So let's see. From 33 to -4, is it increasing? Is that supported by, is that decreasing? Is that supported by the sign of the derivative? Yes. Between -4 and 1? Yes, it's increasing. -4 to 1. 1 to -31, yes, indeed, is decreasing. -31 to 28, yes, it's increasing. So these signs and this symbol, the numerical values that we determine, work well together. So now I'm just going to plot the points, so to speak. So here's 33. Here's -4. Here is +1. Here's -31. And here's 28. Something like this. This is not the graph by any means. I'm just trying to identify what these points represent. Also, can you already tell me -1, -4, what type of point is this? Well, I can't. I mean, I can, but yes, increase goes down. Okay, yeah, yes. So can anyone tell us -1, -4, what type of point we have here? Yes, it's a local min. What type of point is 0, 1? Excellent. And 2, -31, according to this. Of course, you're going to say local minimum. Awesome. But this is the local. Now we want also the absolute. So 33, -4, 1, 31, 28. Can anyone identify if there is an absolute max? Anyone?
33.
Absolutely. So this is an absolute max. We identify these. So now I need an absolute min, if there is one. Negative. Very, very good. So this is a local minimum and also an absolute minimum. Okay, I want us to draw a conclusion before we move on. And here's the conclusion that I would like to put in writing. So this is our page 7. Okay, what does the first derivative tell us about the function? First of all, it gives us the critical numbers. Without finding the derivative, I don't know whether the function has critical numbers. Secondly, it gives us max min. If it has critical numbers, they may become max min, but no, not necessarily. But without the first derivative and critical numbers, I will not be able to find max min. Also, it gives us increasing, decreasing, intervals. Extremely important. Okay? So this is basically the first derivative test. Okay? If a function has a critical number, where the function is defined, of course, and the sign change of the derivative is this, it's a local minimum. If the sign change or the sequence of the sign change is this, then it's a local max. That's the first derivative test. Okay. I would like to, and I'm discussing this with you, we'll make a decision together. The following section, which is 4.2, deals with two theorems, which are very important. They're applications of differentiation. Okay? However, in my opinion, and I let you choose, in my opinion, this section should not be here. Should be after we finish curve sketching, as I mentioned, graphing. Because we're not going to use section 4.2 for 4.3, for 4.4, for 4.5. 4.6, I will not present because it's only calculations with technology. So I will not present this specifically, but if you find a problem that you would like to work on in class, we're going to use this every day. So there is no need for me to just show calculator work specifically for a section because we're doing it all the time. But if you find something that you would like to work on, please. Okay, so we can postpone this for after we finish the curve sketching, which is basically the next 3 sections, or we can continue with 4.2. And of course, the homework will not be due from 4.2 till we get to it. So I'll let you decide. You want to continue with what we are discussing, 4.3, 4.4, and put everything together and graph, or you want to continue sequentially. I'm fine either way. I like my students to be involved in the decision-making process.
I don't have an opinion. I kind of am going off of what you recommend.
Okay, anyone?
Same.
Okay.
Same here.
Okay, so then you are okay with me skipping this and coming back after we finish graphing then?
Yes.
Okay.
If that's the best
Yes.
way to learn it, then yeah.
It's the this will be just a small stop. So for example, we're going to the mountains and we want to stop for coffee. It has nothing to do with our way to the mountains. It's an application of differentiation, but it has nothing to do with us continuing our trip to the mountains. This is continuing our trip to the mountains.
All right, no pit stop then.
Okay, so if we don't need coffee or tea, then we should continue with 4.3. Okay, I will get it ready and we'll come back to it. So what we already covered is, I didn't tell you, this is indeed part of 4.3. Okay, I can't stop. I cannot just talk about critical numbers and not tell you what they mean and then come back in the next section and say, oh, do you remember when we did this? Well, that's what they mean. No, I can't do that. I have to give you the whole thing. Okay, so then we're continuing with 4.3, and as I said, we already started 4.3. So the target here is to sketch graphs, so curve sketching. Okay, so we know what we learned from the first derivative about the function. Well, let's see what we learned from the second derivative about the function. And we have the following. When the second derivative is a positive, has positive values, the function, something called concavity, the function opens up. We say it holds water. When This is one option. The second option is when the second derivative is negative, the function does not hold water. And these are somewhat connected, and I will explain with the second derivative test. If the second derivative is positive and the function holds water, what type of point potentially the function will have somewhere where the function is? Not necessarily, but what type of point will the function have in that interval, or potentially have in that interval? What type of point?
Local min.
Correct. So now if the second derivative is negative, which means the function does not hold water, what type of point? If, not necessarily, yes, local max, yes, good. So this is one thing that we learn about the function, about the second derivative, about the function, concavity. And the other thing is something called inflection point, of course, or points. What does that mean? Okay, here is an inflection point. Or so the inflection point is when function changes concavity from opening down, opening up. So at this point it changes concavity. This is an inflection point. Abbreviated always IP, right here. Same thing, it comes from opening upward and all of a sudden it opens downward. This is another IP. So what happens here is the second derivative is 0 or potentially undefined, and it changes sign, the second derivative, from this, which is negative, to this, which is positive. If it doesn't change sign, even if it's 0 or potentially undefined, this will not be an inflection point. Same thing, it has to change sign, like for the derivative for a max min. Same thing here, from opening up, which is positive, to opening down for the derivative, second derivative. So then this one is an inflection point. So when I determine max min, I study the sign of the first derivative. When I determine inflection points, I study the sign of the second derivative in the same table. Everything happens in the same table. So then I am ready to look at any example you like to pick. Not, we can continue with do the whole thing with graphing also. So this we already completed. As I promised, as I said, this is 4.3. We didn't wait. I didn't wait. I never do. Find the intervals on which f is increasing and decreasing. Of course, we already did that with 3 examples. And find the local max and local min value. This is done. So now I want to move on to an example with concavity, and then examples with everything. Concavity, max min, everything we can think of. Limits, and so on and so forth. So let's choose an example with concavity, which means studying the second derivative, and then we'll continue with the whole graphing. Anyone would like to choose, or I pick?
Someone picked 20 in the chat.
20 in the chat. Very good. Thank you very much. 20 it is. So f of x equals natural log of 2 plus sine x, and the interval is given to us 2 pi. 0 to 2 pi. 20 you said, right? I always check. Okay, so natural log. Okay, so we want the intervals on which f is concave upward or concave downward, and find the inflection points. We're not asked to do the whole thing. Graphing, etc., etc. Okay. Do I have something else in the chat? Oh, that's what it was. Okay, perfect. Good. So please get used to my table, or invent your own, but you have to use a table. Okay, so f prime, f of x, and the second derivative. The interval is given to us. The domain is just this. This is our world right now, 0 to 2 pi. No, I'm not going to study the sign of the first derivative. No, I'm not going to do anything with the function. But this is the table that we have to use moving forward, please. You can make your own adjustments. If you don't like this particular one, just create your own, but I highly recommend it. And I will not take credit for it. Okay, so of course I need the first derivative to find the second derivative. That's clear, I have to, but I'm not going to find critical numbers. I'm not going to study the sign, and I'm not going to do anything else with the function except the function values when the second derivative is 0 or undefined. Okay, good. So we have to find the first derivative. That's our first step. Good pick. Which page am I on? 8. Okay. So let's find f prime. Can anyone help with the derivative? No, I see you cannot see. Not sure what's happening.
1 over 2 plus sine x.
So 1 over 2 plus sine x times
Negative cosine x.
close, cosine x.
Cosine x.
Good. That's perfect. So cosine x over 2 plus sine x. Okay, who cares? I don't need critical numbers. I need to study the sign. I move on directly to the second derivative. So then, second derivative. I have no choice but use the quotient rule. Anyone would like to help with this?
So it's going to be 2 plus sine x times negative sine x.
Very good, awesome.
Minus minus cosine x times cosine x.
Very good, awesome, well done. Of course, I cannot factor. If I cannot factor other than negative in front from both, so now everything is positive, always, always factor, please. So I have 2 sine x. I have plus sine squared plus cosine squared. Very nice pick. Thank you so much. Anyone remembers how much is this? One. Very good. So we have negative, and this is 2 sine x plus 1 over 2 plus sine x squared. Very good pick. Thank you very much. So we have to look at the second derivative being 0 or second derivative being undefined. Okay. So let's start with this. Where will a fraction be 0? This is our fraction. This over this. Where or when or for which x values will this fraction be 0?
When the numerator equals 0.
Yes, I did say 0. Yes, when 2 sine x plus 1 is 0. Good. When it will be undefined. Sorry about that.
The denominator equals 0.
Very good, yes. When 2 plus sine x equals 0. What are the limits of sine? Because we know we graphed sine. We looked at the table. We looked at the unit circle.
1 and negative 1.
Excellent. Thank you. Was it Sean? Okay. Perfect. So then, tell me whether this can be 0. In other words, I'm asking, can sine be negative 2? This is my question, basically.
No.
No. Very good.